Welcome back to the second part of a stream's job. If you haven't listened to the first part of this lecture, I strongly urge you to go back and find part one of a stream's job and listen to that first. Once you've done that, then carry on. Okay, we looked at this figure earlier in the semester in a different module, and I gave a different title on the figure when I used it the last time, but this is figure 1.27 from the PhysRig manual. And there we were talking about the headwater zone, the transfer zone, and the depositional zone, and sort of the geomorphic function and comparing those geomorphic functions between these three zones. I'm showing you this figure again to introduce the concept of a longitudinal profile. And all a longitudinal profile is a profile from the headwaters of the stream or from upstream to the mouth of the stream or downstream. So headwaters to mouth or upstream to downstream if we're just looking at a smaller segment of the overall stream. And that longitudinal profile is a way for us to compare geomorphically changes in the stream. The typical longitudinal profile of a stream is represented by this brown curve on the graph over here. This graph is from chapter 2 of PhysRig. I know it's in the PowerPoint notes section. I've got the graph number, the figure number, but this slope is concave down, and what that means is we have our steepest stream gradients, steepest stream reaches in the upland headwaters areas, and our shallowest, flattest stream gradients down here in the depositional zone. So streams of course flow downhill, but the hills are steeper in the headwaters region, and they gradually flatten out here in the downstream direction. The graph also shows you the change from the longitudinal change in these other processes. Discharge generally increases in the downstream direction. That makes sense, that's intuitive. Channel width increases, think about that. The Mississippi River is wider in northern Minnesota, or in southern Louisiana near its mouth than it is where the stream begins in northern Minnesota. Depth generally increases. The Mississippi River is deeper as you go downstream. The one that's maybe not intuitive on this graph is the mean flow velocity. You may think, well, aren't the fastest flows in the stream in the upland headwaters reaches where the average channel is the steepest? Probably at a reach scale, the fastest velocities you're going to find in the whole stream may be up there. But if you average out over a longer section of the stream, sort of like a 1 mile section where you've got both riffles and pools, so riffles would be in a headwaters area of a larger stream, might be like whitewater where you go whitewater rafting where it's really moving fast. But in between each of those riffles where you have the whitewater, you usually have very slow moving pools of water. It's this riffle pool sequence. And so when you average all that out, you actually have a slower average velocity than you would maybe down here near the mouth of the Mississippi River, where we have very large cross sections with very little friction. So the average velocity of the water is always pretty fast, even if it's not in any one spot as fast as it would be in those whitewater reaches of a headlands or a headwaters area. All right, so I encourage you to inspect this graph a little more closely. The specific figure number for this graph, I think it's from chapter 2. It's in the notes for this PowerPoint slide. All right, stream equilibrium. This is one of the big concepts we're building to in this module and in this chapter. Some of the other reading assignments and media assignments that I'm giving you for the Fluvial Geomorphology module are on stream restoration, which is a growing multi-billion-dollar per year industry that many biologists and geologists are employed in these days. And when we talk about restoring a stream, whether we're restoring its ecological function, if we're restoring its geomorphic function, or we're restoring it for recreational purposes, we need to restore the equilibrium in that stream system. When we look at streams or when we identify streams as not working very well, what we're really saying is those streams are out of equilibrium. So a static equilibrium, and this one is what we don't have or don't want in streams. A static equilibrium is this flat line, no change. The stream is always exactly the same flow velocity, the same channel width, the same channel depth, the same channel slope, all our variables, the same sediment budget. It never changes. That's not what happens in streams. Now, a stream that's in equilibrium with the landscape will usually be either steady state equilibrium or in a dynamic equilibrium. In a steady state equilibrium, the net change over time is zero. That would be the flat line here. But at any one point in time, we're averaging somewhere around that. So what you see here, one step forward, one step backwards, one step forward, one step backwards. Might be wet years, dry years, driving changes in hydrology. In wet years, we may have higher stream flows, greater velocities, greater sediment budgets coming into a channel. And so the channel might grow in one direction to accommodate those big flows. But then we might have a dry period and things sort of reverse, and it all averages out over time. Now, a dynamic equilibrium is where we do have a net change through time over years or decades or centuries. Maybe the stream isn't sizing, it's down cutting because sea levels changed. This happens during the glacial periods. A lot of the water in the ocean gets tied up on these big glaciers on the landscape. As a result, sea level drops and the streams try to erode down to that new base level. Now they'll do that slowly and steadily using a dynamic equilibrium where any one year might be wetter or drier, bigger flows, smaller flows, more erosion, less erosion, but through time they're sort of averaging out to a steady trend in the downstream direction until they get to a point where they've reached the base level, and then they'll come back to this more steady state equilibrium and focus on the difference between steady state equilibrium, dynamic equilibrium, and the fact that streams should not be and usually are not in static equilibrium. All right, Lane's diagram. I love Lane's diagram, or more often it's called Lane's balance. Lane's balance is a conceptual model, and it uses sort of an old-fashioned, the idea of an old-fashioned balance beam scale where you put a known weight on one side and then you compare that to the weight of something else and you try to match those up until the balance centers. All right, well, here what we're doing is we're balancing the water budget for the system, so how much discharge we have, with the sediment budget for the system. So how much sediment is coming in versus going out. And also our other two variables are the size of the sediment, so both the volume or amount of sediment and the size of the sediment, and the amount of water and the slope. So slope is energy. The slope of the stream is where the energy comes from for that stream to do work, to move the water, to move the sediment. The sediment size and the amount of sediment are the friction in the system. So the friction in the system provides resistance to flow. So we have energy that's driving the flow of the water, and then we have resistance to that flow, resisting that movement, causing that energy to be expended. Now the balance of these four variables, and the four variables are listed here, the balance of these four variables will tell you whether the floodplain is going to degrade, which would mean downcut or lower itself, and the channel along with it, or grade. So in a grading floodplain, in a grading stream system, the stream will be building up the floodplain and building up the level of the bottom of its channel because there's an excess of sediment relative to what the stream can carry. And Lane's balance helps us understand how these variables relate and make predictions. And I love to ask quiz and exam questions where I'll say something like, okay, assuming all else is equal, but the slope of the stream increases in a watershed, what's going to happen to the floodplain? All right, so the way you would answer that question is imagine in your mind that the stream slope got steeper. That would mean moving this out over here, which gives it more leverage on this end of the balance, which will pull this side of the balance down. And as this side of the balance comes down, the needle will start to point to degradation. So if we increase the stream slope but hold discharge, sediment yield, and sediment size all equal, the floodplain and the channel are going to have to cut down into the valley, degrade. On the other hand, let's say that we hold everything equal, but we deliver a bigger average sediment size to our reach. Okay, so everything else is the same, but the sediment size just gets coarser. Now think about this. Bigger sediment, well, if you've got sediment the size of a bowling ball, that takes more energy to move than sediment the size of, say, a sand grain. So all else being equal, we haven't changed our energy slope or our stream slope. We haven't changed the amount of water. The water provides mass, and mass can do work when it has momentum. So if we just make the sediment bigger, that means we're going to move this side of the, we're going to move this hook out here to the left. That's going to create extra torque on this side of the beam and move our arrow into aggradation. So keeping everything else equal, but making the sediment sizes larger, we're going to get aggradation. Our channel and our floodplain are going to build up. Now, another way I can ask this question, and I like to ask the question, is I'll say, if stream slope gets larger, what can we do to one of the other variables to counter that so that there's no net change in the channel position or the elevation of the floodplain? So let's say we make our stream slope bigger. Well, one way to counteract that would be either to increase our sediment yield, our sediment discharge, so make the pile of sediment bigger here, or make the sediment coarser. Either of those will provide a counterbalance, literally a counterbalance, to an increasing stream slope. And you can ask this question in any combination. Now, I have produced a separate video for you, bringing lanes balance to life. You get to go to the top secret lanes balance laboratory on the MSU campus. You should check that out. It's just 4 or 5 minutes long, but it shows you a real lanes balance in action. All right, so that brings us to the end of this first lecture in the Fluvial Geomorphology module. Describing how streams work and introducing you to these concepts of equilibrium and the interplay of the 4 variables in the stream system that really cause that equilibrium to occur or to get out of whack. As you move into the upcoming lectures, the other 2 lectures in this module, and all the reading assignments, keep these ideas in mind. Really, a lot of what we're talking about when we talk about streams and stream restoration and stream management, which are big issues in our country and around the world, we're talking about trying to either maintain or get a stream back to equilibrium. All right, thank you for your attention. We'll see you in the next lecture.